us discuss about determination of speed of sound in air at laboratory temperature using the apparatus what is called resonating air column apparatus. So, let us take this one, determination of speed of sound. Resonating air column apparatus. This is what we have even in experimental physics for us. So, what do you find in this resonating air column apparatus? Probably most of you people might have worked out this experiment in your laboratory. The rough sketch of this apparatus I am just giving you here. You will be having a transparent plastic pipe which is connected in parallel to a metal pipe like this of length exactly around 1 meter, and these two are now connected to a water reservoir like this. By means of a rubber tube like this, and you will be having an arrangement to fix this reservoir at any height according to our requirement in that experiment. And this total apparatus is mounted on a vertical stand like this. This is a wooden stand, and this one is called water reservoir, and this one is a rubber pipe, and this one is a metal pipe, and this one is a transparent plastic pipe. This one is. So, a meter long scale also is provided adjacent to it, so that we will be knowing what exactly is the length of that air column which is in resonance with the frequency of the given tuning fork. So, this is the apparatus basically. What we are going to do in this experimentation, if I just remind you in brief, we take water into it, into the reservoir. That water automatically enters into this tube and even this tube as well. Since both the tubes are connected in parallel to each other, level of water in this one and in this one are going to be equal. Same atmospheric pressure that acts on both of them. Since both are open to air, then naturally the heights are going to be equal. We know that point very much. Now, what we are going to do in this case is, we just change the height of that water column. Thereby, by changing the length of air column, we obtain the resonating length at two different positions. The very first one, of course, when we consider, when this is the water level in the tube, that level of water behaves as if it is a closed end of that pipe. That means it becomes now a closed organ pipe. Say whenever the wave is entering this way and reflecting back this way, formation of a node and antinode here when we are observing, that's what we call it as first resonating length. Some amount of sound you can hear whenever resonance occurs, a huge sound is going to be heard, because when resonance occurs, the body vibrates with the greatest amplitude possible. When amplitude increases, loudness increases. So that is the reason why you can hear huge sound out of the system. There only you have to fix the reservoir and its position to be fixed there, and we used to measure the height of that air column or length of that air column, and we call that one as first resonating length. That's what is written as L1. If you are going on continuing the same experiment further by decreasing the level of water, you will be able to hear maximum sound again at some other length as well. When the water level is here, we are hearing the first resonance. When water level is up to this extent, that means this air column's level length is increasing like this, then again I can hear that resonating sound. So what we should understand here is, this length we consider it as the second resonating length. So what is happening in second resonating length? Two nodes and two antinodes are being formed. So in this experiment, we just measure the first resonating length of the air column, the second resonating length of the air column. One is taken as L1, one is taken as L2. Considering the frequency of the tuning fork which is used over there in that experimentation, we can determine directly the speed of sound in air. How? What is the corresponding formula for that? We need to take up. Now in the first case I am dealing with, you can all understand this is the air column. Now we are finding a node formation here, antinode formation here. This we have called it as L1. So yet first resonance, you surely can understand L1, which is first resonating length, that can be taken as lambda by 4. But every one of us are aware of one important, most theoretical concept here. We keep the tuning fork a little above the tube. When you are keeping the tuning fork, say for example here, then this antinode will not be formed at the edge of the tube. Instead, it is formed at the prong of the tuning fork. That means officially, this is the wave that is entering and reflecting and coming back. So whatever is the gap between the position of the tuning fork and edge of this tube, whatever we are having in this experimentation, that gap we call it as end correction. So whenever we write the equations for first resonating length and second resonating length, one should consider even end correction and repeat the equations. So L1, if it is the length directly from the edge plus end correction, that gives you lambda by 4. That is at first resonance. This is the equation we have to take. Similarly, yet second resonance, when second time the resonance is obtained, the second resonating length we can write it this way as L2 plus E is equal to 3 lambda by 4. So what is this L1 over here now? L1 is to be called as first resonating length, and L2 is now to be called as second resonating length. Then from these two I can write L2 minus L1 is equal to lambda by 2. So what would be lambda now? 2 into L2 minus L1. That's one equation we need to remember. Therefore, what is the speed of sound, which is n lambda? So what is that equation ultimately? 2n into L2 minus L1. By using this equation, one can estimate the speed of sound at room temperature. In other words, at the laboratory temperature. Therefore, I just write this one as Vt, that T stands for the temperature of that laboratory in which you have performed this experiment. Now, the moment we have got the speed of sound at that room temperature in air, what would be the speed of sound in air at 0 degrees centigrade? Already we have taken up a rough equation. So we can write this one like this: Vt into 1 minus T by 546. And this T refers to the laboratory temperature as such. So lab temperature when it is T, V0 is speed of sound at 0 degrees centigrade, Vt is the speed of sound at T degree centigrade. Then with this value of V0, you can estimate using this formula Vt into 1 minus T by 546. Till this extent, okay. This is the formula for wavelength we have to remember. This is the formula for speed of sound at room temperature or laboratory temperature we have to remember. And this is the estimated value of speed of sound in air at 0 degrees centigrade as such. But now the question is how to calculate end correction now. How to calculate end correction? That's what we just want. So let us calculate what is this end correction in this experimentation. Say when we write end correction, that of course we represent it by this letter E. What is that value? How to calculate that? Say when first resonance that occurs, L1 plus E is equal to lambda by 4, we have written that. Similarly, when second resonance occurs, L2 plus E is equal to 3 lambda by 4, that is the second equation. Already we wrote these equations while discussing about the experimentation there. What I do now is I just multiply the first equation by 3 throughout. Then the right hand side values are equal, then automatically we can equate the left hand side values. So this you can rewrite it like this: 3L1 plus 3E is L2 plus E. So what we can write from this one? End correction is equal to L2 minus 3L1 by 2. This is the calculation that is required for us to calculate the value of E. This is a formula for the calculation of end correction. L2 minus 3L1 by 2. That is one. There is one more empirical formula, which of course these people have given by considering or by performing this experiment several times using tubes of different diameters, internal diameters I am talking about. So what exactly the case? For an open pipe, end correction of course can be taken as 0.6 times the diameter, or you can even write the same thing as 1.2 times the radius of the pipe. Similarly, when you take this apparatus that is for a closed pipe, end correction is equal to 0.3 times the diameter of the pipe. Now the question is, which diameter? Not the external diameter of the pipe. It should be considered as internal diameter of the pipe. So end correction depends on internal radius and internal diameter of the pipe considered. So you can even rewrite the same this way as well, 0.6 times the radius of the pipe as such. So if you just look at this pair and this pair, since there is only one open end, we can write the end correction as 0.3 times the diameter. Since in the case of an open pipe, two open ends we are having, therefore that becomes 0.6 times the diameter. So these two equations, whatever we have written just now, are empirical formulae by nature. So whenever they ask you to calculate the internal diameter or internal radius of a tube, then you can equate this formula with that, and you can estimate what is the diameter of the pipe, or correspondingly what is the radius of the pipe also you can write. So this is one. Using this concept of end correction, you can even write two more equations. One I will just give you here. For an open pipe, suppose if I write, usually open pipe, when we consider, L plus E is equal to lambda by 2, like we used to write. So what can we write now? L plus 2E into 2 is equal to lambda. That is the equation you need to remember. Exactly like that, for a closed pipe, the one which we have taken up in this experimentation, for a closed pipe, L plus E into 4 is equal to lambda. What for we are taking 2E, we have already seen that one. Open pipe means both sides open, so 2 times we have to take the end correction value. Whereas closed pipe, when we consider, only one side it is open, therefore only one end correction we used to consider. And what is that value of E over there? We can understand it is nothing other than either 0.3 times the diameter in the case of a closed pipe, and 0.6 times the diameter in the case of an open pipe. So these are the equations one need to remember as far as end correction that is concerned. And in this case, resonance is the major concept by means of which we are in a position to determine the speed of sound in air at laboratory temperature. So this experiment, of course, you have to remember just in terms of the equations whatever we have taken up. So that is the only experiment directly what we have, by means of which we can estimate speed of sound in air at laboratory temperature as such.